In this unit, we're going to continue to talk about quantitative data and certain measures that we can use to analyze quantitative data. We've already talked about analyzing quantitative data by looking at their measures of center, by looking at their measures of variability or spread. Another way you can look at quantitative data is where does a data value stand in a distribution in relation to others, which is something people often want to know. I mean, like, for example, you guys write a test, you want to know, where do I stand in relation to how everybody else did? Okay. There's a couple of measures that we can use. So first, we're going to start off with two test takers that wrote two different tests. And this guy is actually the guy that did this lesson, young statistician. He took the SAT, which I believe you're all familiar with, and he scored 1,050, and that's out of 1,500. Okay, or sorry, 1,600. And Guy Fieri, who you may know, took the ACT and he scored a 23. And that test is out of 36 possible points. So right now, how would you figure out, or who do you think has the better score, and how would you figure that out? Yeah, convert them to percent, right? That seems to be. So for Mr. Youngsaver here, he got 1,050 out of a possible 1,600 points. And then we would convert that to a percent. And then we would take Guy there and say he scored 23 out of 36. And he scored approximately, and this is about 66%. And this is about 64%. So one might assume a little better he did on his test. But that's not necessarily the case because we don't know how easy or difficult the tests were. Okay? Maybe a lot of people scored well on the ACT this year, and not a lot of people scored well on the SAT. Maybe a lot of people scored well on the SAT that year, and not a lot of people scored well on the ACT. So that kind of blows these percentages out of the water. It's not really a good comparison, which is why we look at a couple of measures, one being called percentiles. Okay? And a percentile represents the percent of data equal to or less than a certain data value, or less than a reason. So we looked at this example in the last unit where we had the salaries of 12 employees at a company in terms of thousands of dollars. And we want to find what is the percentile, or at what percentile is the person who makes a salary of 43,000. So basically what we want to find is what percent of data values are the same as this employee, or less. Well, how many salaries are the same as his or less? 10. Out of how many total salaries? And what we do with percentiles is we always round them to the nearest percent. Okay? Never leave them as decimals. And this is going to work out to 83. Now, I don't say 83% of the scores are the same as his or lower, but we would say 83rd percentile. We don't say percent. And that's how you would calculate it. So it's pretty straightforward. All you do is list the data from lowest to highest, find the number of data values that are the same as the one you're interested in and less, and then put that over the total number of data values. Okay? Going back to what we did in Unit 1, when we looked at box plots and we looked at first quartile, second quartile, which is the median, and third quartile, what percent of the data, or what percentile, sorry, is Q1? 25th percent. Because 25% of the data values are below Q1. How about the median? 50th, because 50% of the data values are the same or below the median. And then this would be 75th. So going back to the two guys that wrote the standard exams, and this is often information that you're given when you get a score report back from one of these exams that you write. Okay, a lot of times you will be given, actually I think all the time, you'll be given the percentile, which tells you how did you do in relation to everybody else who wrote it. Okay, so if you got, for the SAT, if you got 1600, obviously you scored the same or higher than everybody. But if we go to half of that, if we go to 800, notice like 800 is a 50% score, but it's at the 8th percentile, which means that only 8% of everybody who wrote the SAT scored 800 or lower. Okay, where the actual mark is 50% that you scored because you got 800 out of 1600. So make sure you understand the difference. And then here's the percentiles for the ACT scores. So if you remember from the first page, Mr. Youngsaver was at 1,050. So he was here. Guy was at 23. So he was here. So Mr. Youngsaver was at the 45th percentile. Whereas Guy was at the 69th percentile. So to me, that says that, well, the SAT was harder. Right? Because you could score pretty decently on it. Like he got 2/3 of the questions right on the actual ACT, but he didn't score higher than half of everybody who wrote it. He only scored the same as or higher than 45% of the people who wrote it. Okay, so when you look at the percentile, this suggests that it's more impressive. Because he did better in comparison to everybody else who wrote that specific exam. Okay. Another way that we can show percentiles is something called a cumulative relative frequency graph. So this shows the percentiles. So it starts at the lowest data value and it goes all the way up to 100%, right? Which makes sense. It has to stop at 100 because that represents everybody that wrote it. So to read this graph, I would say, okay, just as an example, if you scored 20, and if I go up here, looks like we're around the 55th percentile. That's how you'd read it. Or if I would say, what was the score at the 80th percentile? I would start up here, draw a horizontal segment over to my graph, go down, and I'm at about 25. So that's how we would read a cumulative frequency graph. So is 18 a good ACT score? Well, it depends on the percentile. So 18 looks like it's about what percentile? 40. Okay. So 18 is at the 40th percentile. How would you describe that score? Excellent, satisfactory, not great. Maybe not great because it's below, he scored, it's below 50th percentile. Okay. So, I mean, these things are generally more challenging. So, you know, you'd almost say it's okay, but it's not great in relation to everybody else that wrote it. So not great in relation to others. And actually, this score-wise, I mean, if you guys got 50% on something, I know how you guys will react to it. Another question using this graph. So you're applying to an elite college, you want to score in the top quartile of test takers. What score do you need? What percentile would represent the top quartile, do you think? 75, right? Because top quartile would be top 25. So that means you got to be above 75%. There's 75%. So we go to 75 on the graph. Go across here and down here. Looks like we're somewhere around 24, maybe a little higher, 22 to 25. So about 24, maybe 25. Should get you in the top quartile. Okay. So that's one way we can compare data values to other data values in a distribution. Another thing is called a Z-score or a standardized score. So what it does is it converts your score into how many standard deviations above the mean you scored or how many standard deviations below. And this is how you calculate. So to calculate a Z-score or a standardized score, you take your data value, subtract the mean, and divide by whatever the standard deviation of the population was. And this is the notation we would use, but don't worry so much about the notation now. We'll get more into that later, but you want to focus on that. Okay, so it's how many standard deviations a data point is above or below the mean. So it is possible to have a negative answer for a Z-score. When you standardize a distribution, like if you standardized all the scores, the mean of the distribution would be equal to 0. And the standard deviation of the distribution would be equal to 1. So we're putting it into a form where we can compare them. So just as an example here, we've got Mr. Youngsaver again, okay? And we've got 2 leagues where the average in both leagues scoring is 10 points per game. However, the standard deviation in the first league is 2 points per game, whereas in the second league, it's 4 points per game. Okay? And he was, which one was he? Oh yeah, in which league would his points per game, which turned out to be 14. Okay? Which one would that be more impressive? A or B? A? Why A?
Because it's a very standardized score.
In A? Oh, sorry, standardized score. Sorry, I knew. Yeah, like, or the standard deviation is smaller, right? If the standard deviation is smaller, that means it's more impressive than this one would be, or the, as you say, the standard of the score. Okay, so in this example, it would be more impressive in League A, because notice, here's where his points per game ends up in a standard deviation of 2, where the data is not so spread out. So these are all the players that had a higher points per game average than he did. Not a lot in this league. However, in this league, because the standard deviation is higher, okay, a lot more players had a higher points per game average. So this is more impressive. Okay, and this is what you look at here. Because these are the ones better than him in League A, but these are the ones that are better than him in League B, which is obviously more. Okay. So more players were better than him. And I'll put that in quotes. Better than him in B than A. Or you could say the converse. He was better than more players in League A than he was in League B. So when we do standardization, a points location depends on both how far it is from the mean and the distribution standard variation of spread. In this case, standard deviation. So it actually gives us a chance, again, it allows us to compare similar things, but that are different quantitatively. So like similar exams, but different scoring systems, like we saw at the beginning. This way we can compare them. So for example, if we go to basketball, like we want to compare sports players in different decades, okay? Well, that's kind of hard to do. But if you standardize everything, then you can get a better comparison, okay? Because right now, when you look at it, well, it looks like Wilt and Michael Jordan are the best, if you just look at the points per game, okay? And then if you look even here, the points per game in their era, well, that's pretty high, but that's a lot lower. So he seemed to do a lot better. So it's almost like, okay, maybe Michael Jordan's the best, but it's kind of hard to tell unless we standardize them. So if we standardize their scores, we're going to take his score, 30.1, Wilt's score, minus the mean of that era, divided by the standard deviation of that era. And when we do that, I'll just give it to you. we get 2.8. So that means, what does that mean if you were asked to interpret it? His points per game is 2.8 standard deviations above the mean. Okay? So the meaning of the Z-score, points per game, you would say whatever points per game is, whatever standard deviations above, below the mean. So his 30.1 points per game is 2.8 standard deviations above the mean, because it's a positive value. Michael Jordan, you take his 30.1 minus the mean points per game in that era, divided by the standard deviation in that era, and we would get approximately 3.6, which suggests that he's doing quite better compared to players in his era than Wilt was to players in his era. And then if we do LeBron, 27.1 minus the average at that time divided by the standard deviation in that time, and we get approximately 3.4, or we get 3.4. Which means he almost did as well as Jordan. Whereas when you initially look at it, you might think, well, it's probably between these two. But you can't just stop there because you're comparing different eras. So standardizing them gives you a more accurate comparison, is the point that I'm trying to make. Okay? All of them obviously were really good because they were several standard deviations above the average in their era. Almost 3 here, over 3 here. That's quite a bit. There wouldn't be a lot of players, if any, above that. However, on the other side, we have a guy who played with the Lakers, Adam Morrison. He averaged 2 points per game in an era where the average points per game was 8.4 and the standard deviation was 5.5. So I just wanted to highlight this one to show you that you can have a negative Z-score. So his is 2.8 minus 8.4, which is going to give us a negative answer, divided by 5.5, which is still going to be a negative answer. And that's going to give us negative 1.1, which is a fair amount below the mean. And probably not a lot of players were lower than that. Okay. Doesn't mean he wasn't any good. Okay. I mean, he'd be better than all of us. So just remember, when you're interpreting a Z-score, if the data value is greater than the mean, you're going to get a positive Z-score. Which means that data value is better than the majority of what's going on. But if it's below the mean, you're going to get a negative Z-score. And again, just if it's positive Z-score, it's standard deviations above the mean. And if it's a negative Z-score, it's standard deviations below the mean. Okay?
So he was not as good as everybody.
No.
Not as good as the other.
No, like, I mean, he was significant. Well, we could see he was below the average at the time, but this really tells us how he compared to the other players, right? Like we knew he would be below, but this kind of tells us how far below he is compared to the others. Okay. And then I think I will leave it at there because This just goes back to trying to determine who was sort of, how do you consider the best player, right? And because there's a whole bunch of different factors at play here. I mean, we could analyze this stuff and we could make arguments. You can make arguments for one or the other. Like, for example, during Will's time, there was no 3 points. There were no 3-point lines. Okay. Whereas in these guys, obviously there's 3-point lines. So in his era, they're taking a lot of shots closer, which should affect your average points per game. So the point is, there's a lot of factors to consider. Okay. But one way or two ways we can compare is through percentiles and Z-scores. Okay.